Welcome back, everyone. It's also another video on the same topic, hydrocarbons, that is part 5. So feel free to interact. My name is Mwiza Chirwa. I'll be taking you through the same topic that we started together about hydrocarbon, which is coming from book 2, chemistry. So let us look at the objectives that we are supposed to achieve by the end of this presentation as well as lesson. So the success criteria that we are supposed to achieve by the end of this lesson are as follows. We are supposed to be able to describe laboratory preparation of alkenes, as well as we should be able to describe some of the physical properties of alkenes. So by the end of the lesson, everyone must be convinced to be able to describe the prescribed success criteria on this slide. So let us start by looking at preparation of alkenes. So we have talked much about alkenes as well as alkenes. In the previous videos, we also talked about preparation of alkenes. Now we'll be looking at the preparations of alkenes, which will take different direction from the preparation of alkenes. So usually the common alkene that is prepared in the lab is ethene. So this is laboratory preparation of alkenes. So there are many methods that we may use to prepare alkenes. One of it is dehydration of alkanol. So later on, we'll be able to look at it in details in terms of the definition of the term dehydration. We already know that ethanol is coming from a group of organic compounds known as oxycarbons, where we can learn much about alcohols or alkanols. That's where ethanol is coming from. So ethene is prepared by dehydration. If we want to prepare ethene using a dehydration method, we still need to have some dehydrating agents. Some of the common dehydrating agents that we use concentrated sulfuric acid, aluminium oxide. We can also use phosphoric acid, and we can also have many dehydrating agents. These dehydrating agents, they act as catalyst in order to remove the OH from the actual ethanol. So we have a question here. The question is saying, describe how we can prepare ethene. So here it's not the actual experiment that we are doing, but we are describing. The procedure can always help someone to go through and prepare ethene from ethanol. So this is just an experiment which is going to be described using some procedures. So the aim of our experiment, remember, we want to prepare alkenes, laboratory preparation of alkenes. Which alkene we are going to prepare in this way? We want to prepare ethene. So we'll start by looking at the aim of our experiment. So the aim is to prepare ethene. Materials that we need a thermometer, we need a sand bath, we need cork, rubber stop, we need delivery tubes, concentrated sulfuric acid, round bottom flask, Bunsen burner, we need a delivery tube, we need a trough, we need ethanol, gas jar, and broken porcelain or sand, which we can use in this case. So these are the materials that we need in order to prepare our ethene. So now let us look at the procedures that we need to follow when we are preparing ethene. Remember, we are describing the process. This description can help us to go in the lab and prepare the actual ethene. So let us go to the procedures. So the procedures are as follows. First of all, you need to measure and place about 20 ml of ethanol in a round bottom flask, and slowly add about 20 ml of concentrated sulfuric acid while cooling the flask. Why are we cooling the flask? Remember, if we are using concentrated sulfuric acid, it's very hot, and the reaction with the ethanol is so exothermic, it releases heat. So if we are cooling, we want not to break the round bottom flask that we are using, and shake the mixture in the flask. So here care must also be taken on how you are handling, because concentrated sulfuric acid is somehow explosive, and it's very hot. It releases heat to the surroundings, so care must always be taken when you are handling sulfuric acid. The setup. So our setup will look like this. We need to have a delivery tube that we are stocking the stopper, our test tube that we are adding the mixture. We have saline here, we have a trough here, then here is where the gas is going to be collected. Now, this is our mixture. So here we can also use cotton to soak all the solutions that we are using, that is ethanol as well as the sulfuric acid, if we don't want to combine them directly for if we use direct heating, we need to soak them in cotton wool so that we avoid the direct heat of sulfuric acid. If not, we can still use a water bath. If we use direct solutions by adding ethanol and sulfuric acid, it means this one was supposed to be in a water bath, such that the heat should be able to heat water from the water bath, and the heat from water will be gently heating our mixture in the test tube here. So you heat gently over the water bath, as I'm saying. Remember our procedure, our setup does not have a water bath, but if we are adding sulfuric acid and ethanol direct, we need to have a water bath, because sulfuric acid is highly flammable and corrosive. It can burn if you heat it direct. Now, if we use a water bath, it means you heat the flask gently using the water bath or sand bath and observe what is going to happen. So, when the mixture of ethanol and concentrated sulfuric acid is heated, an oil liquid called ethyl hydrogen sulfate is going to be produced. Apart from that, there will be also formation of water in that mixture. So here are some of the equations which are describing the whole process when you combine them, the two mixtures. So here we have ethanol is combining with concentrated sulfuric acid. We have applied heat. Ethyl hydrogen sulfate and oil liquid is going to be formed, as well as water is also going to be formed. So this is the chemical equation, just to illustrate more about the word equation, which has been written, explaining more of what is going to happen when you add the two mixtures. And from there, when the ethyl hydrogen sulfate formed is further heated. So if you take ethyl hydrogen sulfate and heat it more further, it decomposes to release sulfuric acid and ethane gas. Now, here we need to understand properly. Sulfuric acid is also going to be obtained at the end of the process. What comes in your mind? If we are able to obtain the same reactant at the product side, it tells us that this one was a catalyst. So sulfuric acid only catalyzed. That's why in the first slides we said it's a dehydrating agent, where it's able to remove water molecule from ethanol. So it acts as a catalyst. A catalyst is a substance that speeds up the rate of reaction without itself being used up. That's why you find that at the end we are also obtaining sulfuric acid. So this one, that is ethyl hydrogen sulfate, which is heated and it decomposes into sulfuric acid and ethane. So this one acts as a catalyst. So we can summarize the general equation about the process later on, but all the gas produced escape from the delivery tube for a few minutes. And why is the gas is allowed to escape? To avoid ethane from mixing with air, and it can explode if it mixes with air. So you allow, it might happen that when you were inserting the test tube in the trough, maybe air was there. So to avoid the reaction between ethane and the air, you release some of the gas first, so that the gas which was there should be moved out, and start collecting the new gas. So the gas which is going to be collected, it will be pure ethane. Collected gas is stored in a gas jar, for other uses. The collected gas can be tested as well to see if it's really ethane, because usually ethane burns with a blue flame when it is exposed to sufficient oxygen. Then you are going to disconnect the delivery tube, connecting the round bottom flask to a trough before stopping heating. Why should we do this? We prevent the water from being sucked back, which can affect our gas. So we need to disconnect before stopping heating. Note, different alcohols are used to produce desired alkenes. What does this statement mean? It means we cannot only prepare ethene. We can prepare any member of alkene so far that we have covered, but that one depends on the alcohol that you use. If you may check on ethanol, the chemical formula of ethanol is C2H5OH, and which tells you that it has two carbon in it. So when you remove water, you still remain with ethane. So when you want to prepare desired alkene of your own interest, you also check on the number of carbon the alcohol that you are using is having, because in that process you are only dehydrating the ethanol. Dehydrating, you are removing the water molecule from the sample. So that one should also be put in an account when we want to prepare any alkene of our interest. So the general equation can be summarized as follows. We have alcohol here, sulfuric acid, and water is going to be released in the process, and we are going to form an alkene. So this is the general equation. We can use chemical equation where this one is an alkanol of interest, and here to produce an alkene of your own interest. But during dehydration, we can use concentrated sulfuric acid as our catalyst or a main dehydrating agent, and produce an alkene. Now, as I said in previous slide, I said after we looked at the description of preparation of alkene, we need to know the term dehydration. So when we are talking about dehydration reaction, it's a reaction where water molecule is removed from a molecule of a compound. So it means during dehydration of ethane, we are going to remove water molecule. After removing water molecule, the sample which is remaining is an alkene. That is the meaning of dehydration reaction. So alkenes can also be prepared using the following methods. It's not only that method, you can also prepare using the following method. Dehydrating method again, but now you are using different acid, that is phosphoric acid. Or we can also prepare an alkene using elimination of hydrogen halide from the corresponding alkyl halide. For example, we have ethyl bromide. This is an alkyl halide, and if you heat it, it breaks and decomposes to ethene and hydrogen bromide. So this is our chemical equation stipulated and showing all what happens. So here we have ethyl bromide, or we call it at bromoethane, and this one, if it decomposes, it produces ethene and hydrogen bromide. So we can also use this method to prepare alkenes. Now, I want to take you into a summary of the process. We need to understand where we said alkenes, any alkene of our interest can be prepared. Now, I want you to, we should be together, we should go through the summary. So, in this summary, we have butanol. We have butanol. Butanol is an alkanol. So automatically the alkene that we want to produce, it is butene. So I want you to pay attention much on the diagrams here. So here is the OH group. Remember, the functional group of alkanols is OH. So we have this OH and the hydrogen here. It can happen that this hydrogen can be the one which is going to be removed, or it can also be this hydrogen which can also be removed to form water molecule here. So when you remove this one, Remember, we said last time that when we are naming alkenes, we also consider the position of the functional group. So that one will help us again. So if this one is being removed, it means we're going to remove one hydrogen from CH3 here. It means we're going to remain with 2 hydrogen here, and this one automatically is coming out. So the hydrogen which is being removed here and the OH combine and form water. That is where water is coming from. Or you can also remove this hydrogen which is here. This one can also be removed and combine with the OH and form water. So it can work in this way. This one just explain the process on what happens, and when you are describing, you can either produce similar alkane but of different position of the functional group, that is the double bond. So if we check here, if we remove one hydrogen from this part, we are going to form but1 but1 we have removed one hydrogen. Remember, this carbon is on carbon number 1, that's why there's 1. So if we remove this one, it means it will be but2, because to find the double bond we have to move between 2 carbons, this one and this one. So it is between carbon number 3 and carbon number 2. So it takes the number of the smallest carbon. So the product is either but1 like this one, when we remove one hydrogen from the first carbon, and it can be but2 if you remove hydrogen from carbon number 2. So this is the whole process of dehydration of alkanol, and it can produce any desired alkene of interest, but you need to consider the type of alkanol that you are going to use to produce the alkene of your own interest. So this process only summarize what happens and the expectation, because sometimes we may think that it can only produce an alkene where the position of the double bond is only once, but it can be shifting depending on the number of carbons which are there. For alkene, you can only have one. For ethene, you can only have one because it only has 2 carbons. But as the number of carbons are increasing, this one can be shifting depending on where you can remove the hydrogen atom. Now, physical property of ethene gas. So it is colorless gas. It has no smell. It is insoluble in water. It has boiling point of 170 kelvins at 1 atmospheric pressure. It is slightly less denser than air. So the general physical properties of alkenes in general. On that last side, we only focus on ethene because ethene is the one which we use as an example on how we prepare alkenes. But we need to look at the general physical properties of alkenes. So we are going to look at the first one as melting at boiling point. So alkenes generally have low boiling points to compare with similar molecule, to compare with alkenes of similar molecular weight. When we're talking about molecular weight, it means we're just looking at with the same number of carbons, the same number of carbons. So what makes it to have different boiling points, different despite that they have the same number of carbons? So this one becomes it's due to weak van der Waals forces. Remember, we said van der Waals forces, these are for weak forces which are created in a compound depending on number of electrons. So since this one has a double bond, it means it limits some of the so it limits a hydrogen atom. So it means it removed one of the electron. Hence, in alkene, we expect to have few electrons than in corresponding alkane. When we're talking about corresponding alkane, we're looking at alkane of similar number of carbons. So, due to the difference in number of electrons, it means now there will also be difference in van der Waals forces created or weak forces created. In alkanes, we are going to have many weak forces created, while in alkenes we are going to have few forces, weak forces created. Hence, in alkenes we are going to have low boiling point. So as the molecular weight increases now, for example, if we are starting from ethene up to decene, the boiling rises due to increase in van der Waals forces. Similar explanation, as we are moving from top to bottom, we expect number of atoms to increase, either hydrogen and or carbon. If you increase the atoms, you are also increasing number of electrons. So if you are having more electrons, you are going to create more weak forces. Hence, that's why we're saying that there will be an increase in weak force of attraction. But it remains lower than that of corresponding alkane. What does this statement mean? It means that, or if we take, for example, butene and butane, butane will still have higher boiling point to compare with butane. The reason is that we have explained here is based now on the number of atoms present and the number of electrons. Alkenes with a double bond typically have lower melting points compared with alkenes with similar molecular weights. The presence of a double bond introduces kinkings in the hydrocarbon chain, reducing the efficiency of packing in solid state and leading to lower melting points. So if you check on those double bonds, you find that they do not have equal strength. The other one is going to have, the first one is going to be more strong than the other one. This also it reduces the efficiency of packing in solid state of that particular compound. Hence, the melting and boiling point decreases to compare with corresponding alkanes. When we're talking about corresponding, we are looking at alkanes of similar number of carbons. So if we're talking about butene, it means we're also supposed to talk about alkane, which is butane. Density. So generally, alkenes are less denser than water, which means that if you add it in water, they are going to float in water. The density of alkenes increases with increase in molecular size or carbon chain, because when molecular size increases, the intermolecular forces are also going to increase, as we explained in previous slide, which makes the particles now to be more strongly held by the nuclear charge, reducing the volume. But when you also increase the molecular size, you are also increasing the mass. Hence, the density is going to increase as we are going down. Since you are going to have bigger mass and small volume, therefore you are going to have bigger values. That's why as we are going down, the density increases in alkanes as well. The reason is what we have explained. The size reduces due to increase in force of attractions, as well as the mass increases. This increases the amount of density as we're moving down. The other physical properties about solubility, they are not soluble in water because they are nonpolar compounds. Nonpolar, it means they do not develop charges. In organic solvent, the alkenes are soluble in organic solvent because in organic solvents like benzene, hexene, all of them are nonpolar compounds. So like, they always dissolve like. Odor as well as color. Odor, many alkenes have a distinctive odor. For instance, ethene and propene are usually odorless. It means they do not produce any smell. But some of the large alkenes might have noticeable smell. So they can produce some smell like a heptene, octene, so as decene, they can also produce some smell. In terms of color, alkenes are colorless. However, some alkenes can form colored compounds when they react with other chemicals. For example, the reaction of alkenes with bromine often result in color change due to the formation of dibromoalkanes. So if they react with other substance, they can also cause an effect. For example, if you add with bromine, it will be colorless because the double bond breaks and allow the atoms of bromine to join and form a dibromoalkane. State at room temperature, lower molecular weights alkenes, that is starting from alkane with 2 carbons up to at least alkene with 3 carbons, that is propene and ethene. They are gaseous at room temperature. Higher molecular weights alkenes, usually they are found in a liquid state at room temperatures. Polarity of alkenes. Polarity, we simply were talking about if the compound has partial charges or not. So alkenes are generally nonpolar substance because they do not form partial charges. Usually partial charges comes in because of electronegativity, as we also discussed in the earlier topics, that is elements and the periodic table. So if they have different electronegativity, the atoms which are joining, they can lead to polarity of substance. But in this case, despite that hydrogens and whereas carbons in alkenes have different electronegativity values, but they form nonpolar substance. The reason is that when you take the molecule of alkenes or any organic compound and cut it symmetrically, they will always give you the same substance, such that the charges cancels one another and form a nonpolar substance. So there is no significant dipole-dipole moments in those molecules. So the nonpolarity influences the solubility as interaction with other substance. What do we mean here? So we're saying that it affects solubility such that it cannot dissolve in other substance, which for example are polar substance, because they would like they have some charges, while these ones do not have charges. So they can only dissolve in organic solvents or nonpolar solvents. Electric conductivity. Electric conductivity is a measure of a material to conduct electric current. So alkenes do not conduct electricity because they are nonpolar molecules. They don't develop ions, so they cannot pass charge from one place to another. Therefore, alkenes are non-electrolyte. Process of alkenes. Dehydration of alkanols. Alkanols can be dehydrated to form alkenes, as we explained. This is an equation which can describe the process where sulfuric acid is a strong dehydrating agent, as well as works as a catalyst to remove water molecule from ethanol to form an alkene. We can also obtain alkenes through cracking of large alkenes. Cracking involves breaking long chain alkenes into shorter alkenes and an alkane and alkenes. Cracking refers to breaking of long chain alkenes into shorter alkenes and an alkene. So we can obtain an alkene through cracking method. So one of the important process in fuel production as well. For example, when hexane is cracked, so cracking, it involves heat as well as a catalyst. Butane as well as ethene are obtained. So if you can check here, we have decane, we have hexane, is being cracked, and here we are producing butene as well as ethene. We are producing hexane. For example, if we go into details, hexane, it's an alkane which has 6 carbons, and when you heat it, it breaks to produce a shorter alkane, which is butane, and an alkene, which is ethene. So the reaction needs a lot of heat as well as a catalyst to facilitate the process. They can also be prepared using hydrolysis of alkyl halide. Alkyl halide can also be treated with zinc or another reducing agent to remove halogen and form an alkene. For example, ethyl bromide, which is bromoethene, can react with zinc, a metal, and it can form ethene and zinc bromide. So this one can be stipulated by the equations which are here. So hydrolysis of alkyl halides. Alkyl halides means you have an alkyl group which is combined with one of the halogen. So you can remove this one, the halogen, and remain with an alkene. Elimination reactions. So you can also prepare an alkene using elimination reactions. Alkene can be prepared by eliminating a hydrogen halide from an alkyl halide. For example, if you have here ethyl bromide, we can remove hydrogen. We can remove hydrogen bromide and form an ethene as well. So we have alkyl bromide, we are removing HBr to produce an ethene, and here we're going to remain with hydrogen bromide. Now that's the end of our presentation. So far we have looked at how we can prepare ethene. We have looked at some of the physical properties of ethene. We have looked so far on how we can prepare other alkenes using different alkanols. We have also looked at the physical properties of ethene. We have looked at the sources of ethene. So reaching that so far, it means we have managed to cover much on the success criteria that we are supposed to achieve. But just to check our understanding, so we have a small buzz session, that is a quick exercise to go through just to check our understanding. Define the following terms as used in chemistry: cracking as well as dehydration. Describe how you can prepare propene through dehydration of alkanols. State three physical properties of ethene gas. Then explain why, before collecting of ethene during dehydration of ethanol, the gas produced first is allowed to escape for few minutes. What is the function of sulfuric acid during dehydration of ethanol? Write the chemical equation for the preparation of ethene through elimination of hydrogen halide. So this marks the end of the whole presentation. If there are some questions, you can reach us through the WhatsApp number here, or you can visit xulendo.org for references and resources. You can visit Excel and Succeed Chemistry Book 2, Achievers Chemistry Book 2, and Target Chemistry Book 2. For the photos that we have used so far, these are the links where you can click and find out more about it. And if you manage to go through the buzz session where there are some questions, you can refer your answers and compare it in our description section.